The theory of small reflections. We have studied in the previous video the basic theory of quarter wave transformer, and we said that the quarter wave transformer can be used to match a real load Z load to transmission line by inserting a section of transmission line section has a characteristic impedance which has the average or the geometric average between Z load and the characteristic impedance of the transmission line, and the length of this transmission line section or transmission line transformer would be lambda over 4 as the center frequency. The previous analysis was based on the input impedance after a specific length of transmission line section. We are going to study the same problem, but going in depth inside the behavior of the waves when it goes from the transmission line to the transformer and from the transformer to the load and when it comes back. Effectively, when the wave comes from the source through the transmission line, assuming that the transmission line has a characteristic impedance Z1, and at the discontinuity between the transmission line and the transformer, which is assumed to have a characteristic impedance Z2, then there will be a reflection coefficient from Z1 to Z2. This reflection coefficient equals Z2 minus Z1 over Z2 plus Z1. This is the first reflection coefficient appears at the wavefront of the wave coming from Z1 to Z2. So, some part of the wave would be reflected by gamma 1 and some part would be transmitted from Z1 to Z2 by the transmission coefficient T21. T21 is actually equals 1 plus gamma 1. So T21 equals 1 plus gamma 1, and gamma 1 is Z2 minus Z1 over Z2 plus Z1. So T21 is 2Z2 over Z1 plus Z2. This transmitted signal is propagating inside the transmission line section Z2 a distance beta L or phase beta L, which equals theta. Then it is attacked by the load impedance. Because the load impedance has a value different from Z2, there will be a reflection coefficient at this end. This would be called gamma 3, and gamma 3 here is Z load minus Z node over Z load plus Z2. Z load minus Z2 plus over Z load plus Z2. When it would be reflected, it will go through the transmission line section 2 until it reaches to the discontinuity between Z1 and Z2. Now the wave is coming from Z2 to Z1. There will be reflection coefficient gamma 2. Here the reflection coefficient gamma 2 when the wave is coming from Z2 to Z1, which equals Z1 minus Z2 over Z1 plus Z2. It can be noted that the reflection coefficient gamma 2 equals minus gamma 1. So gamma 2 equals minus gamma 1. Then some of the field which is already coming to the interface between Z1 and Z2 pass from Z2 to Z1 by transmission coefficient T12. T12 in this case is 1 plus gamma 2, and because gamma 2 is negative gamma 1, T12 it would be 2Z1 over Z1 plus Z2. So some part would be coming here. This part which is passing to Z1 will have a phase shift equal to theta because it have phase shift e to the power minus j theta to go from the intersection between Z1 and Z2 to Z load, and another e to the power minus j theta to go from Z load to the intersection once again. So the total field now in the transmission line Z1 would be gamma 1, the first reflection, plus the transmitted signal 2T1 multiplied by the reflection coefficient gamma 3 multiplied by the transmission from 2 to 1, which is T12, multiplied by the phase shift e to the power minus j2 theta, which correspond to moving around this transmission line forward and backward. Okay? Alright. So this is the first reflection. This is the transmitted signal, propagate, reflected, and transmitted once again. Now, we have some part has been already reflected inside Z2. This part would be transmission 210 multiplied by gamma 3 multiplied by gamma 2. Then it will go back to the load impedance here and reflected back once again by gamma 3 to this point. So we have already another bonus or another bus. This bus starts from gamma 2 multiplied by gamma 3 to reach to this point. It would be multiplied by additional e to the power minus j to c. Now, let us combine all these parts. We have T21 gamma 3 multiplied by e to the power minus j to c multiplied by gamma 2 multiplied by gamma 3 and reach to this point. At this point, it can be transmitted by T12. So we have T12 multiplied by T21 multiplied by gamma 3 multiplied by gamma 3, so gamma 3 squared, multiplied by gamma 2, which has been reflected here, multiplied by e to the power j for theta, and so on. If we are going to take the coefficient transmission T10, transmission transmission 212 multiplied by T21 multiplied by gamma 3 as a common factor, e to the power j2 theta as a common factor, all these as a common factor, the remaining multiple reflection, it would be gamma 2, which is the reflection at this interface, multiplied by gamma 3. So the first one is gamma 2 by gamma 3. The second one, gamma 2 squared by gamma 3 squared. And so in general, it is gamma 2 to the power n multiplied by gamma 3 to the power n multiplied by e to the power minus 2g n theta, where n is from 0 to infinity. This actually is the total field inside the first transmission line Z1. Or, in other words, the total reflection coefficient. So, the total reflection coefficient is composed of the reflection coefficient from the first interface plus the multiple reflections and transmitted signals. Okay? Alright. So, we have the total reflection now. in the form of gamma 1 plus T12 multiplied by T21 multiplied by gamma 3 e to the power minus j theta, 2g theta, multiplied by the summation over n from 0 to infinity, gamma 2 to the power n multiplied by gamma 3 to the power n multiplied by e to the power minus j n c. It should be noted that the magnitude of the reflection coefficient is always less than 0. Is always less than 1 unity. The magnitude of the reflection coefficient is always less than unity. This means that the magnitude of the argument of this infinite summation is less than 1. We know from mathematics that the summation of x to the power n for n equals 0 to infinity, where the magnitude of x is less than 1, equals 1 over 1 minus x. Okay? So, we can replace this summation by 1 over 1 minus gamma 2 gamma 3 e to the power minus j2 theta, assuming that x is gamma 2 gamma 3 e to the power minus j theta, and this term is x to the power n. So the total reflection at the first transmission line would equal the reflection from the first interface gamma 1 plus T12 multiplied by T21 multiplied by gamma 3 multiplied by e to the power minus j theta over 1 minus gamma 2 multiplied by gamma 3 multiplied by e to the power minus j2 theta. But actually we know that gamma 2 equals minus gamma 1 and T21 equals 1 plus gamma 1 and T12 equals 1 plus gamma 2, which is actually 1 minus gamma 1. So we can replace T12 by 1 plus gamma 1 and T21 by 1 plus gamma 1 and T12 by 1 minus gamma 1, and gamma 2 here can be replaced by minus gamma 1, so this would be 1 plus gamma 1 gamma 3 e to the power minus j2c. Now by taking or making the denominator as a common denominator, so in this case 1 plus gamma 1 gamma 3 e to the power minus 2j theta. Here we are going to multiply gamma 1 by this 1 plus gamma 1 by gamma 3 e to the power minus j theta, and we are going to replace 1 plus minus gamma 1 multiplied by 1 plus gamma 1. This would be 1 minus gamma 1 squared multiplied by gamma 3. So in this case the total reflection coefficient would be gamma 1 multiplied by 1 plus gamma 1 gamma 3, or in other words it would be gamma 1 plus gamma 1 squared gamma 3, and here 1 minus gamma 1 squared gamma 3. So minus gamma 1 squared gamma 3 will be subtracted from gamma 1 gamma 3, gamma 1 squared gamma 3. The remaining part would be gamma 1 plus gamma 3 e to the power minus j theta over 1 plus gamma 1 gamma 3 e to the power minus j theta. This is the total reflection coefficient at the first transmission line section Z1. Now let us assume that the difference between Z2 and Z1 is very small, and the difference between Z load and Z2 is very small. This means that the value of gamma 1, which is Z2 minus Z1 over Z2 over plus Z1, is nearly a very small value. It is close to 0. It is not exactly 0, but it is close to 0. And if Z load is close to Z2, so Z load minus Z2 over Z load plus Z2 would be close to 0. So gamma 3 is very small value. In this case, the multiplication of gamma 1 by gamma 3, it would be very, very small value. So we can nearly, approximately, ignore this term, or assuming that this term is nearly zero. This means that the reflection coefficient, or the total reflection coefficient at the first transmission line section, it can be approximated as the reflection coefficient at the first interface plus the reflection coefficient at the second interface multiplied by e to the power minus j theta 2g theta, which is the phase shift due to forward and backward travel along this transmission line section of phase shift theta. So the reflection coefficient gamma is approximately gamma 1 plus gamma 3 e to the power minus j theta. This is known as the theory of small reflections, because actually it is assumed that the reflections gamma 1 and gamma 3 are small values, and according to this fact, we can approximate the reflection coefficient in this form. This form has been done just for a single section transformer. What will be the situation if we have n section or multi-section transformer? Assuming that all these sections has the same phase shift theta, and here we have Z0 going to Z1, and Z1 is going to Z2, and Z2 is going to Z3, until Zn going to Z0. At the first interface, we have gamma naught, which is Z1 minus Z0 over Z1 plus Z1. At the second interface, we have gamma 1, which is Z2 minus Z1 over Z2 plus Z1. And so on, until we reach gamma n is Z load minus Zn over Z load plus Zn. So we have the reflection coefficient at the different interfaces. We can say that the total reflection at the feeding transmission line section Z0 nearly equals gamma naught plus gamma 1 multiplied by e to the power minus j2 theta plus gamma 2. Here we have two thetas, not one theta. So gamma 2 e to the power minus 4j theta, and so on until we reach the n section. We are going to say plus gamma n e to the power minus j n theta, 2j n theta. So this is the summation of the reflection coefficient with the corresponding phase shift delays. The summation of this reflection coefficient with their phase shifts is actually the total reflection coefficient at the feeding transmission line section. Alright? So this is the reflection of multi-section transformer, assuming that the reflection from one section to the other is very small value. Now let us assume that these sections would be symmetric, such that gamma naught would equal gamma n, and gamma 1 would equal gamma n minus 1, and gamma 2 would equal gamma n minus 2. And if we have taken e to the power minus jn theta as a common factor, we can say that in this case it would be gamma naught multiplied by e to the power jn theta plus gamma n, which is actually gamma naught if we are symmetric, gamma naught e to the power minus jn theta, because we have taken e to the power minus jn theta as a common factor. If we inserted this, it would be gamma naught to the power 0 plus gamma naught is multiplied by e to the power minus j 2j n theta. Okay? In a similar way, gamma 1 multiplied by e to the power j n minus 2 theta plus e to the power minus j n2 n minus 2 theta, and so on. Okay? It is interesting to note that this can be replaced by 2 cosine n theta, and this can be replaced by 2 cosine n minus 2 theta, and so on. So the reflection coefficient in this case, it can be represented as 2 multiplied by e to the power minus j n theta multiplied by gamma naught cosine n theta plus gamma 1 cosine n minus 2 theta plus so on, so on, so on. Gamma n cosine n minus 2n theta. If we are talking about n is odd, the last term it would be gamma n minus 1 over 2 multiplied by cosine theta. If n is even, the last term it would be half gamma n over 2. Okay? So, for the case of symmetric transformer, where gamma naught equals gamma n, gamma 1 equal gamma n minus 1, and so on, the reflection coefficient as a function of theta, and as I mentioned before, theta is beta L, and beta is 2 pi over lambda. So effectively, theta corresponds to the behavior of the frequency. So gamma as a function of the frequency or as a function of theta, it can be represented as a series of cosine n theta, where n equal 1, 3, 5, and so until reach n if we are odd, or 0, 2, 4 until n if n is even. If I'm talking about series of cosine n theta, means that I'm talking about some sort of Fourier series representation. This means that the reflection coefficient as a function of theta is represented here as a Fourier series of the angle theta. Now, by tailoring or by choosing the appropriate coefficient, gamma naught, gamma 1, gamma 2, gamma n, all these values of gamma, we are choosing the appropriate coefficients for this Fourier series. And by using the appropriate coefficient for the Fourier series, we can design the behavior of the reflection coefficient as we need, or in the function or in the form of the function that we need. So by using this representation, we can design the reflection coefficient as a function of theta, or in other words, as a function of frequency as we need, by tailoring the coefficients gamma naught, gamma 1, gamma n. Alright? That's what we are seeing. Multi-section transformer. This form represents a Fourier series which can approximate any arbitrary smooth function if enough terms are used. We can synthesize any desired reflection coefficient response as a function of frequency theta by properly choosing gamma n and using enough sections n. Actually, we are going to use this basic theory. We will show how to use this theory to design multi-section transformer for two most commonly used passband response, which are binomial or maximally flat response and Chebyshev or equiripple response. This is what we are going to represent in the following two videos. In the following video, we are going to discuss the binomial multi-section transformer, and in the video after the following one, we are going to discuss the Chebyshev multi-section transform. Okay? Alright.